Okay, today we are talking about shear design of a beam, or I guess a column too. Anything can have shear. Um, Normally we think of it in beams, but columns can have shear as well. So it's really something super simple, actually. So we're just gonna dive right in. There are two limit states for shear and beams. One is shear yielding due to excessive deformation. And two, shear buckling in the web. And we're gonna look at how those come to be in a second. So we have shear yielding and shear buckling. Can I make that U look a little bit better? Okay. So let's talk about shear stress. If you end up going further in structures, you'll learn about shear flow and the distribution of shear stress. You might have talked about a little bit in mechanics of materials. But basically, if we're looking at a solid rectangular section, the shear stress is going to be distributed parabolically along the depth. So this is the height, right? D, depth, height. And it's this kind of parabolic distribution. And the maximum shear stress occurs at the center. And it's 3 times V, which is the total shear force of the cross section. Which, if you're making your shear diagrams, right, V, that's your shear force. And divided by 2 times B, which is the width, and D, which is the height of your rectangular cross section. Now, if you look at a W shape or an I-beam, your width at the edges, at the top and bottom, is considerably wider than the width of your web. The width of your flange is wider than the width of your web. So, since we're usually dividing the shear over that width, there's not really a lot of shear stress in flanges, and it's all concentrated in the web. And you can see here's the equation for your shear stress. It's essentially the shear force, V, divided by your depth of your section and the width of your web. So most of your shear force is carried by the web. So when we're doing shear design of an I-beam, we only care about the web itself, right? D, the depth of your section times the width of your web. And so we can rewrite this equation down here. Your shear stress or your shear force is your, hold on. Your shear force is equal to your maximum shear stress times your depth times the width of your web. So again, just know that when we're doing shear design, we're going to focus mostly on the web. This is a generally, I mean, it's kind of funny if you think about it. In bending, what you really care about are your flanges, because not much is going on between the flanges, which is why you have I-beams to begin with. And then for shear stress, it's the opposite, right? Only thing you care about the web. The flanges are just along for the ride. So shear strength. What will control excessive shear design? I think where will we look to control our design? Well, oftentimes, right, if you think about let's say we have a simply supported beam with a concentrated force in the middle. What is my, then a reaction on either side? My shear diagram looks something like that, right? Where you have your maximum shear forces near your supports. So that's where we're going to look for our design, right? Or our design forces. We have large concentrated forces near our beam supports. Actually, that's not what that means. I meant if you have a large concentrated force near your beam support. Right. If, say, you have a large concentrated force like that, now you're not going to have a whole lot, right? You're going to have a really high shear at the end. These are shear diagrams, can't you tell? They're so good. So what will control my design if I have a large concentrated force near my beam support? If I have a notched coat or a hole in my beam, right? If you don't know what that looks like, I'm going to get rid of this lovely thing right here. If, as we get into, sometimes when you get into near a connection, a beam gets cut off a little bit to allow room for the, what it's attaching to, right? This is kind of an elevation here. This is your I-beam. Maybe I'm a beam connecting to a girder, right? So this right here is how I'm going to cope my beam. And you see that reduces the my cross-sectional area of my web, right? Which is what I'm designing based on. So now not only am I likely having a higher force because I'm coming into a support, a higher shear force, but I've reduced my area. Same thing if there's a hole in the beam or if you take a notch out of it somewhere. You're reducing the area that resists the shear force, so you have to take that into account. If I have a thin web, what do you normally think of when you think of something being thin? Like long and skinny columns, that usually leads to buckling. So a thin web might have some buckling going on, some shear buckling. So we have to keep that in mind. And then we also need to keep in mind what type of connection it is. If it's a rigid connection, such as a moment frame, you're going to be having moments and shear at the same time in those connections. So that may reduce your capacity. Okay? So if I'm looking at quantifying would be a better word, quantifying my shear strength, I'm going to assume that shear and moment are independent. Right? So we're not adding up the stresses involved. Because like I said, most of the concentrated stresses from bending or moment are in the flanges, whereas most of the stress due to shear is in the web. So they can be considered independent. The web carries the entire shear force. Those flanges are just along for the ride. even though there was actually like a distribution of the stress along the depth, we're going to assume that we're going to actually average it. Right, that was the equation that we just had a second ago. I'm going to take that shear force, and average it over the area of the web, which is my depth times my thickness of my web, to get my shear stress tau. I'm using tau for shear stress, and hopefully you guys did this in mechanics and materials, right? The sigma was for normal stress and tau was for shear stress. If I'm going to calculate my yielding stress, they use the von Mises yield criteria, which is a way of calculating the yield stress based on, it's a criteria of quantifying yield stress. It's usually like called an equivalent stress as well. If you guys go further and take advanced mechanics and materials, you start getting into that. But what that basically means is I'm going to use the equation, my shear stress associated with yield is my yield stress, Fy, right? That Fy 50 KSI, 36 KSI, whatever type of steel you're using. And I'm going to divide it by the square root of 3, which equals 0.577 times Fy. Fy is my yielding normal stress. Sigma y. Again, that's like 50 KSI. Often for like A992 steel. So if I'm calculating my yielding, right, we're going to talk about this in a minute, but if I'm calculating my yielding, I'm going to find out what the yield shear stress is, multiply it by my web area, and I'll get my shear force that I'm allowed to use. Right, that's simple enough. Well, right now we're still in the theory, but we'll get into design quickly. So what is shear buckling? So let's say I'm looking at the web of my I-beam, and I'm going to look at a little element right here. And it has shear stress acting on it. Gonna look at a little element. It has shear stress acting on it down on this side and up on this side. And then I draw the corresponding ones on the top and bottom. And that is the shear stress tau that is acting on that little element. Well, if you guys did any type of more circle, I hope you did it, in mechanics of materials, you would know that if I rotated that element 45 degrees, whereas this is pure shear stress, that's the only stress acting on it. If I rotate that element 45 degrees, I now have pure normal stress. I've translated that shear stress into normal stress, and it becomes, still using red, compression and tension. Right, we're gonna draw this a little bit more. Right. Right. It's a little refresher in mechanics of materials. My little element has shear stress acting on it. And if I take one of those shear stresses, vectors, let's see, I can make it into a 40, I can get the components at 45 degrees. Same thing with, let's see, which way? That way. And then, is that right? No, I don't like this one. I think this one would go more like that, yeah. Right, so let's see, all my horizontal ones. Are that, and that, and that, and that. Right, those are all tension. And all my vertical ones are compression. Yeah. I wonder if I could draw that better. So those are compression, compression, or tension. So I took my shear stress vectors and broke it down into components at 45-degree angle, which means I've translated my shear stress into compressive force and a tension force. The green ones are all supposed to be parallel and the purple ones are all supposed to be parallel. So, right? That's how I went from here to here. Pure stress, pure shear stress to pure normal stress, and I have compression. Well, right? So I have my tension pulling my element, and I have compression squashing it. And what do we have when we have compression? We have buckling. So if I'm designing for shear buckling, there can be buckling in the web due to shear. Right? Shear buckling due to compressive stresses. Which are transformed from my shear stress, and the extent of the shear buckling, like how much it happens or how likely it is to happen. Depends on, well, what does buckling usually depend on, right? The slenderness. Right, the height of the web and the thickness of the web. So I have shear buckling caused by shear stress, in which I transformed it into tension and compression. The compression leads to buckling, and it depends on how slender my web is, whether or not it's going to buckle. Okay? Now, one way to help combat shear buckling is to add stiffeners. Which this is the side view. If I look at this, right, in the cross section, I'm going to add, this is my I-beam, I'm going to add some type of plate. To stiffen, literally stiffen my web. Because what happens if I add a stiffener there? Well, this stress field doesn't have anywhere to go once it hits the stiffeners. So this section is buckling restrained by stiffeners. And this section, the only thing that's stopping that buckling, that the extent of over which that stress goes, is once it eventually hits the flanges. So the only thing preventing buckling there is the slenderness. So we can add stiffeners. Stop clicking the little button. Okay. Add stiffeners to control buckling. And what those might look like are vertical plates that are welded to the web to limit the area that can buckle. Yeah, and it doesn't have to necessarily attach at the top or bottom flange. It could really just be like a plate that looks like that, right? Doesn't necessarily have to be at the top and bottom. But it could. Okay. Look at that. The stiffeners, however, could create something called tension field action. Which would actually provide additional shear strength after the web buckles. So we talked about the compression in one direction due to shear stress, but there's also tension in the other direction. So red is my tension. By my web. And if you think of the stiffeners as a connection point, right? We create an equal and opposite force for that tension force. And now that my web's not doing anything, it's buckled, so it can't hold any compression force. The things that are holding the compression is the stiffeners. Right? I wonder if I could make that a different blue. Let me see. Right? I have compression in my stiffeners. And then if I draw the equal and opposite at the nodes, you can maybe kind of see this looks like a truss, where my vertical members so I have a tension field within, right, this is my tension field. Let's see. My webs have a tension field. And this creates basically a truss. Right? Where my vertical members, my stiffeners, are my compression members, and the webs themselves have become the tension members. Right? Did I say that right? Compression, stiffeners are the compression members, and which are vertical, and the tension members are the web. This phenomenon does not occur at an end panel of a beam, because then all of the shear would just be going straight into the support if it were buckled. or the support isn't providing enough, it doesn't become compression member. It also doesn't apply to widely spaced stiffeners. You would imagine the further apart it gets, the less likely that you're going to have these tension fields occur. It's just going to kind of, the tension, once it buckles, it's just going to, the whole thing is going to buckle, and the tension gets kind of spread out over the entire width of the web between the stiffeners. And also, tension field action is generally used in built-up sections design. A built-up section is where you create your own section, your own I-beam or your own channel or something out of plates instead of using standard sizes. Okay, so now we're going to get into design. That was all of shear theory. We've got shear yielding and buckling of the web, which you can help prevent with stiffeners or by making a less slender web. So shear in the manual, if we're looking back in the spec, we're going to go look at chapter G. And we're actually, even though we just did all that talk about tension field action, we're going to stick to G2.1. It says right here, let's see, that my phi factor for shear is 0.9 except for G2.1, which is where we're going to stay. So we're doing members with unstiffened or stiffened webs, and G2.1 is, oh, it doesn't even say it. This is why I have the wrong PDF. It's supposed to say, if you look in your manual, shear strength of webs without tension field action, with a phi factor of 1. So I'm assuming I'm not going to have tension field action to help my design. Right, so I've got my phi factor is equal to 0.9 except G2.1a, where my shear fear factor is 1. Okay. If I go and look at G 2.1, I-shaped members and channels, shear strength of webs without tension field action. I have the shear strength based off of the von Mises criteria. If you remember, that was 0.577 Fy. It was Fy over square root 3, which is about 0.6 Fy. So we just rounded it to the 0.6. And then we have a reduction factor to account for shear buckling. And that is how buckling is considered in shear design. It's not accounted for as a separate limit state. So I have my shear stress associated with yield, the area of my web, which is the depth times the depth of the entire section. So when we're talking about that, if you go and look, which we can go look in a second, but we're talking about the depth of the entire section. Like if it's a W18 by 76, your depth is 18. We're not talking about just the height of the web minus the flanges. We're talking about the entire depth, right? I'll just draw that just for fun. The entire, this is the area that resists shear, the entire depth, so D, and that's a terrible W, and the width of my web. Still kind of a bad W. Let's see. So my stress times my width, this is the nominal strength that you then multiply by that phi factor. So if we're sticking to G 2.1a, webs of eye-rolled members, if I have a slenderness ratio, now this is where we're talking about the height, which is different than the D. If I have a slenderness ratio less than 2.24 times E over Fy, right? That square root E over Fy is similar to when we were doing buckling, local buckling of like flanges and webs. Same thing here. It's a factor times the square root E over Fy. It happens to be a factor of 2.24. But if my height of my web, which is right, this is kind of like the height. It says clear distance between the flanges, less the fillet at each flange. So it's not D, it's H, but it's still that width. That's my slenderness ratio. If it's less than the 2.24 square root E over Fy, then basically local buckling won't occur. Or not local buckling, web buckling. I'll have a phi of 1 and that CV factor of 1 no web buckling. Okay. For all other I members and channels, that means I-shaped members that have a slenderness ratio greater than or equal to greater than, not an equal. Greater than that 2.24. Or if you're looking at a channel, that means I go back to my G1 to tell me my phi factor of 0.9 because it said right, it said except for 2.1a phi is 0.9. So now we're in 2.1b, so my phi is back to being 0.9. And my CV1 factor, which means I'm going to have buckling, right? But I'm gonna maybe have buckling if I have a slenderness ratio greater than the one specified in 2.21 or 2.1a, and maybe a channel is more likely to buckle too. So my CV1 factor, I get to calculate it. It's going to depend on my H over TW, my slenderness ratio, web slenderness. And this KV factor. Coefficient. Ignore that little I that's right there. So I get to go down to G2.1b if I have if I have a built-up section, or a rolled eye with a higher slenderness ratio. Right, back in 2.1a, it said a rolled section if I have a built-up I-beam. Or a rolled I-beam with an H/TW that's higher. I have to do some other calculations. First, I have to look at my web slenderness to determine, will it buckle? And if that answer is yes, then I get to calculate this KV value. How much will it buckle? How much? So I check on if it'll buckle by comparing my H/TW, right? If it's less than 1.0, then it's not going to buckle. Hold on. Where is that? 1.1, but notice I have this KV factor in here. This means it's not going to buckle, and so I got a CV of 1. If it's 1.1 to 1.37, I'm going to start buckling, and I got to calculate a CV. And the shear buckling coefficient there's different ways to calculate it. If I don't have any stiffeners and my H/TW is less than 260, I can use 5. Otherwise, I have to calculate it this way. Right? I'm just on page 16.1-71. That is not the right thing. I'm not in PowerPoint. Okay. Okay. Let's see. So this is those equations that are in G2.1b. Right. If I get to have a CV of 1.0, no buckling. Oh yeah, I guess that there's 14th edition. I need to get my 15th edition PDF. So what I just showed you was wrong. These are right. These are from the 15th edition. I got to calculate this KV factor first. The KV factor is calculated depending on the ratio of how far apart my stiffeners are. If there's no stiffeners, or how far apart they are versus that clear distance of my flange of my web, right? If I'm looking at the side of a beam with transverse stiffeners, right, that's the top and the bottom flange. If I have stiffeners, where'd that go? That's the distance between them. If I look at a chart, we love our buckling charts, right? We have my slenderness ratio of my web. Remember, it's a ratio, it doesn't have units. And then my CV1 factor on the y-axis. Get to draw in this lovely right here. That is my 1.1 square root KBE over FY, which is my slenderness ratio between yielding of my web and the presence of shear buckling. Right? It's basically the graphical representation of the one more. This one. All right, less than 1.1. You got no buckling, so yielding is going to control. Greater, you're going to start to have shear buckling. Okay, I'm going to do one example. And then we'll do the other example on Thursday. Right? Everybody got this down? So I have a W21 by 50, KSI, a little yield stress 50 KSI, and it's subjected to a dead load and a live load, uniform distribution. Make sure that this works for the shear. So first, calculate my loads, right? I notice it includes my beam weights. I don't have to add that extra 50 pounds per linear foot. And what do I get? Boom, 8.8 kips per foot. I get to go to my shear and moment diagram. Let's see. shear, my maximum shear occurs at my supports, WL/2. Alright, you should be able to see it right here. WL/2. On page, 3-208. Right. WL/2, so W 8.8 kips per foot. And length is 20 feet. Divided by 2. 88 kips. Maybe you can do that in your head. So, would a 21 by 50 be able to hold up 88 kips per foot? So let's see. If I go back to chapter G, my first question is, so this is a rolled I-beam. Right? Rolled means somebody else made it. I didn't put it together with a bunch of plates. It came out of the mill that way. So I have to calculate my H/TW. Luckily, that should be somewhere in my book, right? Let's see. W shapes. Looking for a 12 by 50. On page 1-26. Oops, that's not what I wanted. Let's see, W 12 by 50. My H/TW is on my next page. 12 by 50. H/TW 26.8. Is that right? $26.8. Why do I have 49.4? Huh. $12 by 50, right? 12 by 50. 26.8. It's weird. Alright. You see where I get that 26.8? Now I need to compare that to 2.24 square root E over Fy. What, 29 1000 KSI over 50 KSI. So let's see, 26.8 and 2.24. $53.9. It's less than, so I get to stick with G 2.1A, webs of rolled I-beams with H over TW less than 2.24 E over FY. Right, no buckling. My phi V equals 1.00. My CV1 equals 1.0. So my phi V VN is phi V times 0.6 FY times my depth times my width of my web times my CV1. So I get 1.0 times 0.6, 50 KSI. Let's see, I gotta go look up those values. That's where it's always like, maybe should have looked it up before. Let's see, 12 by 50. My depth is 2.2 technically. I must have used a weird, 21 by 50. Is that what's going on here? Oh my gosh, 21 by 50. Okay, I feel way less crazy now. There is a 12 by 50 though. I was like, why are my numbers totally different? That's why. H over TW for a 21 by 50. Let's see, 21 by 50. There it is. H over TW of 49.4. Okay, I'm 21. Apparently I was dyslexic for a second. Okay. So let me go back and change that. I'm still less than 53.9. Let's see, so I still get to use G 2.1A. So it's fine. Other than I'm just going crazy. Okay. So 21 by 50. My depth is 20.8. My thickness is 0.38. So 20.8 inches times 0.38 inches. So my CV factor is 1. Phoebe. Sounds like I'm saying Phoebe, but not well. 1 times 0.6. 50. 237 kips. Which is greater than my VU of 88 kips. So everything's good. Would a 12 by 50 have worked? I mean, 6 times 50 times a 12 by 50 would also have worked. Good to know. Yeah. Got like 135 kips of capacity in there. Good. So you notice we used the spec. We could have also used the beam part 3. Maybe. Right? If we go to the beams, if we go to the beginning of the beam section, part 3, page 3-1, available shear strength. Gives you a little summary. We can actually look in the tables 3-2. All right, table 3-2 also has a phi v in it. Notice it's X. It's assuming that your I-beam is standing looking like an I. Major axis is not turned on inside. So this is based on the depth of your section times the thickness of the web. A little bit harder to actually find them in there, right? Let me see if I can find a 12. No, I'm 21 by 50. Let's see. And actually this number might not be correct because, see, 237. Okay, that's what we calculated, right? Oh yeah, because we were in G2.1a, which is probably why it still works. 237 kips. So that is one way to calculate shear strength, and we can do more the next time we talk. So let me know what questions you may have. I hope that was pretty self-explanatory. Thanks.